Electricity affords luxury to society. Though from light bulbs to computers, it is a constant job to generate the exact amount of power to meet demand 24/7. Too much electricity can kill a machine, too little is useless. Electrons are tiny and temperamental, so how can we predict the seemingly unpredictable? A circuit is like a network of pipes for electrons to flow, and each device is like a turbine along those pipes that needs flow to spin and work. Charge is measured in coulombs, and each electron carries a tiny but identical slice of charge. Alongside this charge, the amount of pressure pushing the electrons through this pipe is known as the voltage, and the amount of charge flowing past a point at any second is the current. Therefore, the derivative of the charge with respect to time t is the current in a wire. Electrical energy is not transporting the physical electrons from generator to user, rather a wave-like energy. A generator pushes the first electron at the start of the wire, increasing the voltage, pushing the next, and so on. Most grids then invert the voltage, pulling the electrons instead before pushing them again in a sinusoidal magnitude of pressure. This is known as alternating current because the pressure changes in a sine wave. Therefore, the amount of charge flowing past a point on the wire, hence the current, also oscillates between forwards and backwards, though not necessarily in identical phase to the voltage. The current can have a phase lead, where it reaches its peak before the voltage by some fraction of a period. Engineers generally choose the maximum voltage and current in the grid. However, the action of AC means the true voltage is constantly oscillating. At time t, it is equal to the maximum voltage multiplied by the sine over omega t, omega being the frequency at which the voltage oscillates between pushing and pulling. Capacitors temporarily hold the charge in a circuit. The relationship for these is the charge held is equal to the capacitance multiplied by the voltage of the circuit. If we differentiate both sides with respect to time, we're left with the current equals the derivative of the voltage with respect to time multiplied by the capacitance. Capacitance describes the storage size, which according to laws of differentiation operates as a constant term. When using alternating current, we already know its voltage involving sine, therefore its derivative involving cosine multiplied to the capacitance is the current flowing into the capacitor. Consequently, current reaches its peak value a quarter of a period faster than the voltage, hence its phase lead. Trigonometric derivatives provide precise values for current at any time, and by this definition, current indicates the rate of change of voltage. Thus we can calculate how fast the capacitor will fill with charge, how a circuit will lead to changes in volts and amps, and more broadly, how electronics respond to adjustments in these values, since current is impacted by the magnitude changes over time, not only by its magnitude at a single moment. Ultimately highlighting that current depends on how quickly voltage changes, not just in its value, which is why calculus is essential for understanding real electrical systems.